So moving quickly on, we are convinced that this equation is the really foundation of what actually we want to do. Consider that well, there are many examples. I will go for Electron primarily because it covers many flavors of beam dynamics. It covers a lot more about the focusing in the transverse direction and in the longitudinal direction as well. And of course, it has a distinct electron source. But there are two different scenarios in which clastrons can be operated, at least physics-wise. Consider that we have a gap here. Whenever there's a gap, we have electric field seeping out. Electric field cannot exist within the metals. If we have a plate which is charged and we have another plate which is differently charged, there is an electric field. So if we have an oscillating circuit which has a certain oscillating frequency and it is applied with a certain voltage as compared to the electron gun, there is quite a possibility that there will be oscillation in this region. The field within this region will be oscillating. Okay. I should have mentioned that this U0 is the energy of the electrons that is provided by the electron gun. So electron guns are, of course, that's why they are called guns. They accelerate the electrons and then they are injected in this region where this guy is facing an oscillating potential. U is the potential. And then after some time, they go through this drift space. Forget about what happens to it. We will discuss in detail in the longitudinal dynamics case. When this guy comes here, the resonant a certain oscillator which is tuned in such a way that can resonate can have a feeling of passing by electrons. The electrons which pass through the second cavity, the second gap, this gap is acting as a cavity where the electrons can actually donate their electric field to the outer match circuitry. I asked a silly question: why drums have membranes, why certain musical instruments have membranes, and while others have some cavities? So maybe we can develop an analogy here. These are the two resonators that are tuned, taking into care the frequency and the amplitude, the potential in it. But this frequency has to be low in a sense that the electrons can pass from this point to the other without significant change in the amplitude of the field. That is sort of quasi-static. In that case, the gaps can be coupled with matched lumped circuits. Okay, this is low frequency. Drum is a low frequency instrument. Okay. Yeah, this is a low. This is the case where the frequency is low. The oscillation frequency. What if we have a case? Okay, this thing can be discussed more because this U2 is depending upon the bunches. Consider that the electrons which pass through are subjected to the electric field, and electric field is reorienting or rearranging the electrons in space. They are bunched. Do you have idea of bunches? Just to give us a flavor, a short flavor. I will discuss it in detail in longitudinal dynamics. Electrons coming from the electron gun are continuous, sort of continuous. But the electric field can squeeze them in space so that the charge density is higher at some point. Okay, that is shortly can be perceived as a bunch. So once that bunch passes through the gaps, the current which is injected and with the current which is felt in the second gap is basically a function of this, what you call chi, I don't know, psi, okay, thank you, psi. What is this? This is very important. This is basically the argument of the first order Bessel function of first kind. This guy is basically the bunching efficiency of your instrument. Okay, bunching is very important. Bunching is the key to generate higher current in the second gap. Okay, I will discuss in detail, but I would like you to first appreciate what is this J1. This magenta line is J1, and it has a maxima at around 1.84. Excuse me. 1.84 is basically the limit, is basically the mathematical limit of how efficiently we can bunch and how efficiently we can have the current in the second gap. Are we clear? Again,
this is for circular cavity, right?
That's
why you have Bessel functions.
Yes.
Otherwise, you will have sinusoidal.
Yes, of course. We inject this with the current I naught, and some current is felt here as well. Okay, that current is I, but that current has an added feature that it is no longer a continuous beam. It is coming in packets, the bunches. The bunches.
Charge accumulation.
Charge accumulation. Yes, thank you. Charge accumulated. But the charge accumulated has a mathematical limit that this can have a certain value, not more than that. And in fact, this bunching parameter is depending upon the distance which the electron travel, this distance d from this gap to the center of the next gap, this d, the velocity it has gained, the potential that we apply, they all together make one this bunching parameter, and of course the frequency with which.
Yaqub, is there a frequency in the first equation W, or just sine t or omega t?
Yeah, I'm sorry, it's a typo. There should be.
Typo.
Thank you. I'm sorry. So, but this again, yeah, I've corrected it in the next one. Sorry, thank you very much. I will correct it in the final draft. But the thing is that one should appreciate that the final voltage that is felt in the external circuitry is a function of the bunching parameter, the frequency, the velocity, and the distance. So bunching is limited. What we can do, we can increase the velocity of the electrons, perhaps. We can play with the distance. So these are all the recipes that physicists would design, and engineers will make them realized. Okay. So this is basically the efficiency. What if we have the frequency, higher frequencies are injected in the things? Well, what we do, I'm not going into the details because we got shorter in time and have perhaps a lot to cover. The thing is that we have to replace those external circuits, the lump circuits, with antennas and RF waveguides. That's where the high frequency clastrons are there. It's a violin, by the way. That one was drum. This is violin. Violin has a cavity. It has an opening, and sometimes you also have those musical instruments. They have waveguides attached to them because they operate in high frequencies. In higher frequencies, the resonance is peculiarly different. That's why we have to attach the ports where the frequencies can come in or go out. And by the way, it should be easy for you to understand why we have to place antennas at the periphery of the cavity, not inside. It's one of the homeworks that you should be able to answer. Yeah. So this pretty much this cartoon is the simplified picture of modern day klystron. We have electron guns which are injecting electrons in a cavity where we have to seed this thing with an RF signal. RF signal gives the velocity modulation, the collection of the charges, and those charges, when passed through the second cavity, they give their energy in terms of electromagnetic field. But this electromagnetic field, although it has the same frequency, but it has a higher pointing vector, the magnitude of the pointing vectors. That's why it is called amplifier. And then the electrons are dumped, of course. If you have oscillators, then these can come back and back and forth. The oscillators are different, but perhaps I will not touch them. So the space charges, we are convinced by this point that we need high current. We need very high space charges, and that space charge or the charge is originated at the electron gun. Okay, so we need high current. Now we are after high current. We are like eager to generate high powers, but this comes at a price. We have to pay the price. Whenever there are high electron densities with bunch profiles, the field, wherever they go, they create disturbance. They create a disturbance. So yeah, this is a problem. And this problem is, once solved, will bring us a step closer to the gun design, the electron gun design. So consider that we have no charge. It's a French word, without space charge. We have very fine distribution of the potential. These green lines are the potentials. And by the way, you should now understand that the potential lines follow the geometry of the plates. This is very important. This should be understood. And the electric field vectors are basically the perpendiculars drawn on those potentials. So if I release the electron at the point where I'm pointing now, the electron will gain the energy. But what if we have a lot and lots of charges? What will happen? They have their own field. They will basically, disturb the already existing electric field, the potentials, in fact. What is the worst consequence of this thing? The worst consequence is that the electric field vector, which are perpendicular to the potential, will no longer be directing in one direction. Okay, it will be causing a divergence wherever the electron will be gaining energy, no doubt, but they will not be a collimated beam. This is a collimated beam, very precise, but what if it is not focused? It is going everywhere. It is not a beam at all. It's not at least what we want. So we have to modify this guy and this guy in order to create a focusing effect. Maybe now this makes sense. Why we have the focusing electrode surrounding the source. Okay, but first we have to quantify. We can't go without any educated guess. In fact, it's not a guess at all. It is well-defined physics. So consider that we have potential lines which are donated by this phi. This Laplace equation very finely, without source, very finely describes the potentials. No problem at all. They can be electric potential, they can be magnetic potential, whatever. What if some charge come into place and we have vacuum? The equation is different, and it is worst when the charges are moving. When the charges are moving, the velocity comes from the potential. Of course, the charges will interact with the potential lines, and they will gain velocity. And what happens if the potentials are themselves disturbed? The velocity will be disturbed. Okay. So the shape of the electron trajectory depends on the potentials. This is the baseline or the punchline of the electron gun, or any source, in fact. Consider that from one point to the other point, we have an alpha potential like increment or decrement, depending upon the potential. What happens that velocity will be weighted by the alpha squared root, and the charge density will be proportional to the alpha cubic 3/2 power of that thing. I want you to appreciate this thing. We have those lines which have no charge, and from point to point the potentials are different. Of course, this is higher potential, and as we go to the other electrode, the potential value is different. If, for example, from one point to the other, the alpha is the increment, then the velocity is incremented by the squared root of this particular constant, and j is basically altered with this thing. So we actually, if we connect a power supply between these two, which we have to, so the potentials are different, and the current density we feel is actually the 3/2 power of the potentials which are there. This is because we have introduced this current density J, the moving charges. Okay. This is the same thing. Due to shortage of time, I may go to the end result. This is what is very important. This is the Childs-Langmuir law, which is the foundation of the high current electron guns. What does it say? I would like you to go through the simple mathematics, which in 2 slides, which I've skipped. We have a space charge density. The electric field lines are disturbed, the potentials are disturbed, and due to this charge, there is a dip. The potential at the cathode is changed. The electric field at the cathode is changed. So this, in fact, the cathode is defined as the value as the position in the space where we have zero potential. Okay, but due to this charge, the potential has gone sub-zero. So in fact, the cathode has shifted virtually from its original position. That position is called virtual cathode. In fact, if you are familiar with the thermionic emission simulations in CST or any other big solver, you have to define the position of this virtual cathode. In fact, all the emissions in this case are felt that actually they are not coming from cathode, they are coming from a virtual cathode. Okay, and the potentials are changed with the 3/2 power of this current density. So the Childs-Langmuir law puts the limit on the current density that can be achieved in case of thermionic emission, and of course the potentials that has to be applied should follow this law. In fact, there is a characterization of the electron gun. Once the electron gun is manufactured, we try to find out the current it is extracting. The current extraction, if follows this potential that we apply between these two electrodes, we say, okay, the the space charge is there. That's why we have this sort of experience. Okay, so take-home message is we need electrons. We need electrons and lots and lots of electrons if we want to have a source of electrons to generate the electromagnetic radiation. But this opens up the Pandora box. We have to have a source with high current density, which means that high current density should be accelerated to very high power. With high power acceleration, the longitudinal bunching should be accomplished. Unless they are bunched, there's no use. It's an explosion, nothing else. And the transverse dimension of the beam must remain within limits to avoid the beam loss. We cannot allow the beam to expand uncontrollably. You have to confine it. So associated systems must be there. We have to operate this in ultra-high vacuum. We have to have low voltages and high voltages power supplies, which are very stable. In yesterday in afternoon, we had a very good lecture about the modulators and the power supplies. The ripples, I asked a question there, but yeah, ripples should be minimum as possible. And that's why only then this fourth point is satisfied. Physicists are very peculiar. They are very particular in their senses. That's why they ask very ideal thing, but ideal word is never achieved. So this comes to the conclusion of the basics of the physics that we would like to have if someone wants to design an electron source. In fact, if someone wants to design the maybe electron gun, in fact. So now I will cover this point. We will switch to this point tomorrow, inshallah, but let's discuss about the transverse dynamics of the beam, transverse beam dynamics of the beam, and the longitudinal beam dynamics of the beam, how beam behaves when we talk about the electromagnetic radiations or the electric radiations or the magnetic field. Perhaps you have noticed that without mentioning, I have changed my word from electron to beam. Maybe it's inevitable or it's just coming from my intuition. Electron, not every electron bunch is a beam. Beam has a very particular definition. And any discussion about beam dynamics should actually start with the definition of what a beam is. How do we define a beam? Now I need that gadget, the tablet. Please excuse me if I am not able to use this. I'm used to those boards and things, but I'm using it for the first time. So excuse me. Here. So look at the screen. Consider that we have a source and we have electrons coming out of it. Not all electrons or particles will have same position and same energy. Rather, there will be a distribution of the things. Some electrons will have maybe this is a particle, which we call an ideal particle. Look at the screen. The red dot is an ideal particle, a reference particle, a hypothetical particle, and all others are just surrounding it. No matter, some particles have emitted earlier than this red dot, and some particles are emitted after this red dot. I have to draw a plane, okay, where I plot the position and slope of this distribution, okay? and I place my, that's what happens. I place my ideal particle at the origin, and all the rest are surrounding somewhere here. For example, the particles which are higher in velocity and ahead of this will end up in the first quadrant. Is it? The particles which are slower but they are ahead maybe end up here. The particles which are slower and behind will be here. And what about these particles? They are behind, but they are moving faster. That is a distribution. So a beam is defined as a collection of the particles which have similar position and momentum coordinates. In fact, we have to define a state vector in X, in Y, in energy, and in phase. These four entries of the vector define the transverse position, and the rest of the two define the longitudinal jargon of the beam. So can I switch to the, I will come to this if it's not clear. I hope it's a bit clear. Is it? Switch to the slides. Okay, so it's a nice cartoon. Thank you. No, I'll manage. Thank you. So we have a particle, an ideal particle, and a vector which is pointing to this certain distribution. That certain distribution has some coordinates in space, and of course some coordinates in energy space. Together, if I just rearrange it, this ideal particle will have a certain position in X direction, a certain slope or the velocity in X direction. X prime is basically dx by dz. Z is the propagation direction, the direction in which the beam is moving. And these two guys here are
dx by dt or dx by dz? X prime.
dx by dz. Yes, it's not the velocity. It's not the. That's why I call it slope in a different thing. We will talk about the co-moving coordinate system. That's where the point will become.
We change the screen share from it. Then zoom. From zoom, they see that one.
Okay. Yeah, this one. Okay. Thank you. So we were defining our beam. Maybe we have to click it again on this. So this makes the trace space. The trace space is basically the slope and the position. The first four entries of this vector are defining the beam in transverse direction, and the rest of the two are defining the beam in longitudinal direction. Longitudinal space is basically the time entry where the phase comes into play, the energy we suppose that the energy is gained in one direction. It's in a simple jargon. Okay, so this vector is our tool for the next 1 hour or so. In fact, this vector will be dealt with in every beam dynamics thing. We have to define, first we have to define a beam. A beam is some collection of charges which have similar momentum and position coordinates, and mathematically they can be defined using this state vector. Okay. Now, again, there is a choice of calculating the propagation of wave from one point to the other. It's just like I'm standing on a platform and a train passes by. I can see that the train accelerates or the car or the bus accelerates or stops, whatever. The driver who is sitting inside the train or the bus also experiences this thing. So what makes simpler calculation is that we have to shift the coordinate system on the ideal particle. I just mentioned the ideal particle. It's not any particular particle. It's just a particle, a hypothetical particle that is following the reference or the ideal path. It is the path that what we want the beam to follow. Okay, this is the path which we want our beam to follow. So all the rest are relative positions of the family. All the family members are just vibrating or circulating around this particle. So if you just conceive this thing, okay, this is the transformation. If you want to shift your frame of reference from the moving frame of reference to the lab frame of reference, then you have to apply this transformation. But maybe this is not important. Okay, so do we calculate every position? Do we calculate every momentum of every particle? This will make life very difficult, especially if you want to calculate in codes. Even in fact, by hand is impossible. As the professor mentioned yesterday, there's n number of particles, and n squared is some density. In physics, we call it density of states. So are we bothered about every particle? Or we can make things a bit simpler. Yeah, we can make things simpler. This is the trace space which I draw a few moments ago. We have an ideal particle sitting at the center, and all the rest are just distributed in this space. It's not real space, it's a trace space. We can always draw a boundary, which is, in our case, can be represented by an ellipse. This ellipse is basically the transverse representation of the beam. The boundary of the particles, maybe this particle will gain energy or lose energy and come from this coordinate or coordinate to this coordinate. These particles can gain energy and they're shifted to the different coordinate, but they will remain inside this boundary. This boundary is called the envelope, just like the envelope of the letter that we receive. We used to receive those letters when I was a child. Officially, we still do. But envelope is something which holds the things inside. So this beam envelope can be very interesting. The vertical projection on the x-axis is basically the size of the beam, the beam spot, footprint of the beam in real space. Okay. So there are different things which tells us how divergent the beam is, how it is tilted, and what is the area of the beam in phase space. We have basically characterized or defined the beam in transverse plane. A transverse plane will have an elliptical distribution of the charges, and these mathematical definitions will basically tell us the complete picture of the state vector. Remember, we are after a state vector. Okay, this state vector, has a state vector, this has a state vector, but in fact, we are not bothered about individual state vectors. We will be bothering about this beam envelope, the beta function. It is not relativistic beta. I'm sorry about the notations, but yeah, physicists have only few letters to use. So this epsilon is very important. This we call the emittance. Remember, in the morning I talked about emittance. Emittance has many definitions. In fact, when I was starting as an accelerator physicist, for the first 2 years I was so confused. Now I can be less confused and I can make you lesser confused. The thing is that the emittance is the parallelism, how the beam is parallel, how parallel the beam is, how collimated the beam is. Mathematically, it is defined as the area of this ellipse. The area of this ellipse is called the emittance, the RMS emittance. Root mean square. It has a statistical definition. All right, so the job of a beam transport guy is to preserve this distribution, take this distribution, pack it into an envelope, take this envelope, accelerate it, and deliver it to its destination. It's just what we call delivery guys. We call it delivery guy in Pakistan. I don't know what you call it here. It's a sort of job of a delivery guy. So delivery guy is not supposed to have a look on it, but it can rearrange if someone wants to pop out, if something living inside, and for example, cats or dogs or something, but it has to confine this thing. So this boundary has to be preserved. The area of the phase space ellipse must be preserved at any cost. This is one condition. Envelope must not be tempered. It's not easy. In fact, it's very difficult sometimes. Okay, so these are the mathematical definitions. I assume that you are familiar with some statistics.
Shape of the envelope is changing.
Yes, it's changing.
But area is fixed.
Area is fixed. Yes, I will discuss the theorem in next slide.
Newman theorem.
Lively's theorem, yes.
Yeah.
Lively's theorem, yes. It's Lively's theorem, yes. These are the statistical definitions. You can write a short program in MATLAB or in Python. If you like, I can give you a homework problem. I have data of this sort of distribution, and you guys, if you want, you can plot this distribution using these formulae to have this distribution. This will give you a flavor of how the beam looks in phase space, in the boring space. But it's equally very, very, very important. What if we have a particle distribution here? Consider it as a distribution, not a single particle. And it is transported from this point to the other. What happens? What changes, as the professor has mentioned? Is there any change in the vector that we feel during the transportation, or it will remain the same? If you carefully look at this cartoon and use some trigonometry, you will come to these equations, and these equations can be readily put in the form of a matrix. What is it? This is an old vector which was acted upon by a certain transformation to have a new vector. This old vector is the state vector at position A. I call it old. It has a Sx as a position and S as a slope, x prime. And this transformation M is some transformation, hypothetical transformation. Someone has tied a knot on the envelope or just put it in a van or whatever. And this transformation M acts on this vector, and the destination vector is basically the combined action of these two matrices. Okay, so we use matrices to actually define the transportation. Matrices are the backbone of the beam transport. We have vectors, we have vectors, and we multiply that state vector with every matrix that would come along in the path of the transportation. In fact, we define as a distinct, a unique matrix for every part of the machine. For example, electron gun has its own matrix. The space without field has its own matrix. We call it drift space. Magnet has its own matrix. Different types of magnets have their own matrices. Accelerator or RF cavities have their own matrices because these matrices are actually the functions of different things. I will show you the MATLAB program. These are the functions which act on a certain thing and generate a new thing. Okay, so transportation matrices are inevitable, and this cartoon shows that if the electron source has generated a state vector, in this it will first go in a space where there is no field. It will be a matrix with drift space. Then let's say, for example, if we have XY deflectors which just guide that beam into a straight path, then of course this will have a vector or a matrix of its own. Then there's a drift space. Then there's an electrostatic acceleration. If we have an accelerating cavity, for example, multi-cavity klystron, and then we have quadrupole magnets. Everything comes in order, step by step. This vector will first face this, and the multiplication of this two will generate a single vector. A new vector, a state vector will be generated. It will have the order of this thing. By order means the number of rows and columns. It has 4 rows, 1 column. When it's multiplied by 4 matrix, the resultant will be 4 rows, 1 column. That's a simple linear algebra. Okay.
The formulation is similar to ray optics.
It is,
but it assumes that all the transformations, related to the components.
Yes, you're right. In fact,
real case, real life, they are not all linear, transformations.
Yes, you're absolutely right. In fact, that's why we call it particle optical elements. In fact, this concept is borrowed from the optics. Yeah. So
but that assumes, the components are linear. They behave linearly in terms of coordinates.
yes, yeah, we assume
they are not always, so this must be valid in a certain region,
Yes. For example, that's why I'll talk about paraxial ray approximations. The rays are quite close to the principal axis in case of paraxial approximations. I will talk about it tomorrow. But as professors here, is there any law that the transformation follows? Yes, there is law. You can change the phase space ellipse. It is, for the sake of simplicity, drawn in the form of parallelogram under a linear transformation. You can change the area, but you cannot change. You can change this shape, but you cannot change the area. The net area of the ellipse or any geometrical shape must remain constant. This is called Lavallee's theorem, a theorem which makes the foundation of the beam transport is that, okay, you have an envelope, you can roll it, you can elongate it, but you cannot change the total area of the envelope. So that's what we see. We have an ellipse, we can transform it. The net area must remain constant. This is the utmost condition for beam transport. Okay, this is a very interesting cartoon. if someone will ask you or me to design an electron gun, what I will ask in return? I will ask him, tell me the state vector of the beam that you want at the target. What is your requirement? Accelerators, klystrons, traveling wave tubes, maybe, they're all designed in inverse order. First, we determine the state vector at the target. This is the starting point. Tell me what you want. Then I try to design the acceleration system, the beam emittance preserving system. After all these calculations, I can check what sort of state vector I would need at the electron gun. The electron gun is designed at the end of the physics. Okay, it's a bit confusing. Let me go through it again. Someone wants a high power klystron. They need high charge density. They need high current. They need certain spot. Then we need electron gun for the system. So we have to back calculate using this mechanism of matrices in order to what the client wants is this. What we can do is this. We have to define all the things which are involved in between. Do you have any question? So in fact, beam dynamics is interesting in the way that you have to understand every bit of every physics of every bit of the machine. So in that case, I would go to a simulation that I have prepared using MATLAB. It is basically, I will go to the last slide. It is, I'll come to this point. Consider that we have a beam coming out from this point. We have magnets, we have everything involved, we have dipole magnets. Someone was asking about dipole magnets. Every bit has their distinct transformation matrix. Distinct transformation matrix means a distinct function that will act upon a beam which has certain beta, certain emittance. Once you have gone through that exercise, you will be appreciating these numbers. These are basically the 6 vectors. This defines the complete state vector, which will be acted upon by these points, and this green line is the beta function. I will give you a short demonstration. Sorry, I have to switch to my laptop. It may take a couple of minutes. So I need your help. So basically, just what I have done is a very simple thing. I have translated this whole beam line in terms of matrices, which are representation for the particular magnets or the drift spaces or any energy devices that are involved, and I inject my particle, and then the particles can be transported from one point to the other. And remember, I will not bother about the single particle. I will bother about the envelope, the beta function. Okay? Can I join?
Yes, you can share.
Okay.
Thanks.
Okay. What you see here, these are the magnets. This is the quadruple magnet. They are in pair. And we have a dipole magnet, which is basically like steering the beam, from bending the beam, in fact. And then we have three quadrupoles. They are used in triplet formation for certain reasons. And we are supposed to focus the beam. This is the beam spot at certain locations. For example, this is a dog leg. I will talk about it in detail at the end of the lecture, just to have a flavor of it. But these are just you guys should just look at these numbers. These are the alpha and beta and the emittance of the beam, which I calculated it using a different software. This is called Parmela. And what happens when I change the strength of my quadrupoles? These sliders are basically the currents, the power supply currents that are being connected to the magnets. When I change the current, the strength of the magnetic field will change, and the envelope, you should look at the envelope. It should change. Okay. It explodes. The beam is gone. I have to adjust the strength of my magnets if I want to focus the beam at a point. I cannot exceed the limits of these boundaries. These are my boundaries, apertures of the accelerator or the machine which I want to pass through. So I have to keep that beta function, the transverse beta function, within limits. Unless I do it, I'm lost. To give students a flavor, what if I can change the drift spaces between them? These are the drift spaces. I changed the drift spaces, so you should be seeing a different beam now.
I'm not. Now, don't.
Can you double click? Okay, bigger.
Sure. So if you change the sliders here, for example, I change the first drift space, which is here. I change it, take it to 1 meter, maybe. Sorry, my laptop is not very fast. So the drift has changed, and the beam has also changed at the end. So you have to play with every bit of your machine in order to gain access to the target. The moment I changed, the beam spot changed into an ellipse. This is the beam spot in real space. So it's basically the projection of the beta function on the axis. So we'll talk about this in detail when we come to a particular case of FELs. Professor yesterday talked about FELs. This program was basically written for a similar machine. In fact, this is similar to tar lava, the bunch compression for tar lava, or for FEL. So I go back to the slides.
Slides.
Yeah.
Stop the sharing.
This will be more interesting when we have discussed. So,
Right, did you talk about how to define this waterfall?
yes, we have to define different functions. If you guys are interested, I will show at the end the code which I have written for this machine. You have to write your own code. I mean, this is not available off the shelf. Okay. So consider now let me assume that we are familiar with the transverse thing. Okay, we'll come to this point again, but now let's talk about the longitudinal character of our being. Do we have time? I guess.
We can take a break and then we will continue.
How much time do I have left?
2 or 3 minutes.
What time is lunchtime?
No.
No, I mean
can-
lunchtime. What time is lunch?
12:30.
I don't know. It depends on you. If you want, we can continue until 12:30. We
Okay,
only have 1
okay.
hour. Yeah?
Okay.
Is it possible? Okay. So it's a long class. Oh. So longitudinal beam dynamics. Remember, now we are concerned about the last 2 entries of the state vector. We will change the phase. We will change the energy of the particles. See what happens. This is the governing equation. People call it Finoffsky's equation. It has lots and lots and lots of entries and lots of interesting physics. We have a charge Q that is subjected to E naught. Forget about this thing. In case this is the case, then it is simply the electrostatic accelerator. But unfortunately, or fortunately, we have a time varying electric field. This electric field has been subjected to a certain phase, weighted to phase. The field has been confined in an environment. Now I'm going to launch my particles in it. What will happen? And this length L is basically the gap between the two points. Remember the cartoon I showed. That's why I always need a board, because once we have to switch to the diagram. Consider that we have a cavity. A point is where the particle enters, and the point where particle leaves. The gap between these two is the accelerating gap, the gap where the electric field is established, the gap where the field is maximum. All right, there. So this length L is representing the active length or the gap of where the electric field is. Okay. This cos phi is the phase of the field. I go against this for a moment. Synchronous particle. I will talk about it. Consider this is the phase of this electric field, which has a maximum at electric E naught. Okay, but this E naught will keep on moving in time. It is subjected to this Q charge, but as the charge will feel electric field, it will start accelerating or decelerating, and it will be moving from one point to the other point, from 0 to L in our case. But while it is transferring, the electric field is also changing. It will not feel the same electric field at every point. Is this point clear? Okay. Because we have a time varying electric field, imagine that these fans are modulated. They're not moving at a constant speed. The moment I start from here to there, the fan in my line will change their speed. So I will feel different fields, different thrusts. So that different thrust will in fact contribute another factor in the equation, that is the transit time factor. This is a very important factor, which actually tells us that you can not always have acceleration. Depending upon the point where you inject, point in time where you inject, you can actually be feeling acceleration or deceleration. If you are too late, the phase has changed. The phase has gone to the negative point. So the electric field has reversed the polarity and it is no more in your favor. Okay, so this transit time factor, I have a cartoon showing. All these things will actually change the kinetic energy W of the beam. Remember, we want W because we want to generate Poynting vector. That's what our aim is. All right, let's talk about how the beam is presented. And now comes the concept of synchronism. You have to be at the right place at the right time. This is the one phrase we always talk about. For example, if I want to go to mosque for Fajr prayer, I must be there at Fajr time. I cannot be there for noon or evening. So this is the right time for the ideal particle. Notice that the ideal particle has now changed its phase space, and now it is being glued, fixed to a certain phase. Some particle who are very fast will be entering the cavity when the electric field has not risen to its maximum. Is this early particle point clear? For example, I have a group of people. I'm at the middle. Some people are ahead of me. Some guys are behind me. They're moving faster and they're entering in a room. And they feel this is the electric field that is being phased. The early presenters, the early comers will face the field which is lesser in magnitude. Okay? What about those who are behind me? When they're here, the field has already risen to a certain higher values. Okay? And then there will be a peak, and there can be other people who are coming too late when the field is already decaying. Is it clear? What will happen? This synchronous particle will gain a certain amount of energy. Okay, all of them will gain, in fact, all of them will gain. A certain amount of energy will be gained by a synchronous particle. The particles which are moving faster will gain lesser energy. Is it clear? Because they were presented at a time when the magnitude of the electric field was less. And those who come late will be given an additional incentive. They will be given, okay, come. What will happen? At some point, those who are ahead of me will come nearer to me, and those who are behind me will come nearer to me as well. So this will be a bunching effect.
Charge accumulated.
Charge accumulated, yes. Thank you again. So the accumulation can happen here. And what about this thing? Okay, they are gaining at most the same energy, but they will be lost. They will be lost. I have a different cartoon, but it's a bit difficult to understand. Let me grab a glass of water before we go there. What about this cycle? Okay. What about this cycle? The particles which are presented here will be lost altogether. Will be lost altogether because they have different polarity. They have not, they're too late. They're too late. They're too late. Too late to be accelerated. They're in fact decelerated.
What will be effect on the system? How those particles will affect on the system?
Yes,
Almost half of the particles, or 3/4 of the particles are lost.
yes, you're right to ask this question. Thank you very much for asking. In fact, this can be very aggressive if such thing happens at very high energies, because those particles who are very high and they are decelerated, they will be back bombarded. They will damage the system. That's why people gently collect the charges, and then the bunch itself is presented on the right face here. All the rest are forgotten. I mean, we have pre-bunchers.
Gently bunching.
Yes, then gently bunching.
Gently.
We have pre-bunchers, which are called subharmonic bunchers. We have harmonic bunchers, and then the actual machine. Unfortunately, this doesn't happen in commercial machines, but this is an utmost requirement in FELs. FELs cannot survive without subharmonic bunching and harmonic bunching. Okay. So before we move on, we will be talking about this transit time factor. Imagine this particle enters a gap and travels from this point to the other. And while it travels, it gains the energy. And also the beam, so the electric field is decaying. This is a model. If we plot this equation with respect to the gap and the velocity of the particle, it tells you that unless you have a certain value, you will be ending up in the negative value of this transit time factor. What will happen? That this will be negative and the net energy will be decreased. I go through this again. You have to be very quick. You have to be very quick. This beta is now the beta of the particle. Before the field decays, you have to quit this gap. You have to quit this gap, this beta. This gap should be tailored. This gap should not be very long. Very long. Because if it's very long, the particle will have a longer time to travel and the field will go negative. So this particular time period is very important. This particular, it doesn't have a unit of time, in fact. It is a factor. It is called transit time factor. So you have to travel from this point to this point, but keep in mind that you have to be very quick. The gap should be shorter so that you will feel nearly a constant field instead of rising and falling field. So you have to be nearly DC sort of regime. Okay, what happens? The bunching. Remember, this morning we had this bunching parameter, the value of what is 1.84. Now comes this point. We have synchronous particle. The late particles will gain very high energy. I'm sorry, this is not very obvious maybe, but you can always have the presentation. The cartoon makes the sense. The synchronous particle, for example, will have the particle which is presenting at the zero crossing will have a constant slope, the bluish one. The ones which appear early will have lesser energy. The slope will be smaller. The ones who come very late will be gaining very high energy, so they will catch up at some point. Okay, is this diagram clear? I have just drawn the slopes of individual particles synchronous particle, early particle, late particle, and unstable particle. Okay, if you just imagine what will happen when these particles come across the time varying electric field, what happens is that they will have different velocities. Depending upon their different velocities, at some point they will be bunched. Let's go ahead. What will happen that those who are moving faster will cross me. Those are slower will again be left behind me. Will it happen? So at certain point, until certain point, the bunching will last, the bunching effect will be felt, and after that point, the debunching will start. Okay, let me make a cartoon again. This time I will use a paper. It's very difficult. I mean, is this point clear? Or we can use some bottles again. Consider that these are the 3 bottles, which are, this is the synchronous particle. Thank you, sir. Thank you very much. Thank you, sir. This is the synchronous particle. The particles are distributed somewhere here. Okay, the early particle is ahead of the synchronous particle, and when they pass through this gap G, the cavity, the early particle come closer to the synchronous particle due to this distribution. The early particle gains lesser energy. The synchronous particle has a certain energy. What about this late particle? Late particle will gain much energy, and it will come closer to this distribution. This will make a single bunch. Okay. What about this unstable particle? Unstable particle will come closer, but it is far. It is very far. It's so far that we cannot regard it as the part of the family. Okay, the bunch family is, it's called, in fact, we call it tail. It is called tail of the bunch. Oh, I'm learning quickly. So what happens after some time, this drift space that we saw, the drift space adds to the velocity reorientation of the bunch. This is called velocity bunching or the ballistic bunching. Oh, my writing is too poor. Ballistic bunching. I've written it in the slides. After a certain point, they come very close. What if I let them go beyond that point? The particles who have gained high energy will be actually leading after that point. And the particles which gain lesser energy, we call E, will be shifting at the end of this distribution. So this is the maximum bunching point, and then the bunching starts to decrease. We call it debunching. Is that clear? Okay. Now, before we switch to the slides, let me prepare something else. This is the diagram which we just saw, which shows the slopes of the particles. It has a certain slope. The particle which is late will have a higher slope. Okay. The particle which came early, which will have a lesser slope. So there will be a bunching point here. As after a certain distance, they will be bunched, and then there is again debunching. Debunching. This particular diagram is called the Applegate diagram. I don't know why they call it Applegate. Applegate diagram. It tells you the distance that is required at a certain velocity for for particular machine. For example, if you have a cavity, you want to determine the distance which is suitable for the bunching, you will be plotting basically an equation. I will show it in a while. It is like this. For a certain energy, you can always determine this distance t, and depending upon your requirements, you can tailor the amount of distance and the energy, in fact, that is required for efficient batching. One thing that I would like you to consider is the following, and it is very important. I would request you to pay attention. Consider that this is the signal, the RF signal, and we have a particle which is synchronous particle. We call it synchronous particle. It is here, and this is the real space. And now I'm trying to draw longitudinal phase space. Similarly, similar to what we developed the transverse phase space. Here we have phase, and here we have the energy. Okay, the particle which will be early, will have higher energy. This is early particle. This is synchronous particle. It will be, sorry, the early particle will have presentation somewhere here. It will be behind the phase and less in, but higher in energy. Similarly, if you have a late particle, I'm sorry, this is early particle and this is late particle. The late particle will have the phase difference, but it will be here. After some time, this will lose energy and this will gain energy, as we saw in this diagram, the Applegate diagram. So we will have these particles actually revolving kind of behavior around this synchronous particle. Okay, this will make a boundary which we call a fish or a separatrix. Separatrix is basically a phase space well, a potential well, which gives us a flavor of how particles move in phase when they are subjected to different types or different magnitudes of the electric field. So this is basically called the separatrix. Every particle which is inside it is the form of a beam. The particles which are here or anywhere are basically unstable or just the part of the satellites. So in any case, for RF redistribution, RF acceleration, you guys have to be within these separatrix limits. You have to be within these separatrix limits. I think we can switch to my slides if possible. Sorry to bother you again.
Please stop the sharing.